Hi guys, if you have ever used the TradingView platform, you might be wondering that it would be nice if somebody could tell me what the big players are doing that you can know by the options chain, and you want something like this trading insights, then that's what we are going to discuss today. Hi, my name is Rajin Chaudhary, and you are watching Net Ganesh channel. So this is what I have built, and we will see the step by step how to build this kind of an TradingView options copilot. So basically, what it does is, like say when I'm looking at the Nvidia Corporation, for example, looking on the TradingView that okay, this is the overview. I can see the details here, but I want to know what the big players are doing, right? So then I'll go to the options here, and then I'll have to interpret this option chain data. So I thought that it would be nice if we can summarize it. We can build a copilot. So that's what we've done here. So when we're looking at the NVIDIA here, this copilot will automatically pick it up from this ticker here from the URL. And it will tell us that, okay, the current market price is this one, market sentiment is bearish. This is based on the volume, right? There is more uh, sell volume than the buy volume, then based on the open interest and volume data. So major resistance is 245 strike, major support is 180. So if I look here, like sometimes if I want to verify this thing, I try to go to the Yahoo option chain data. For example, on the support side, let's check the support first. On the support side, we see 180. So if you look at 180, we see that okay, there is a 14,000 uh, volume here. So that's what it's showing here. And same thing for the strike resistance level. So if you go on the call and then say 180, it shows at 180. This is the what is that? 245. So 245, it shows there is a 40,000 volume. And then it gives us the insight, like in plain English, that there is a heavy call writing detected at 245, making it a tough ceiling for the bulls, and the downside, massive put accumulation at 180, and this acts as a rock solid floor. So this is, I mean, it has interpreted it for us. So we know that where the big players are, putting the heavy buying, selling heavy options here. Right? This is mainly the sellers, the market makers. So what they are doing here. So it will give us the insight. So this is what we have built here. And so if we check this for another ticker, the way it works is I'll just show you the final product first. Then we look at the the how it is built. So if you look at the Apple, for example, then when we click on the Apple here, so our this is a Chrome extension. This Copilot will pick up that now we are watching Apple stock here on the TradingView, and it will tell us it will give us the insight for the Apple. So here it says okay, it's 312 the current price, resistance is this, support is this, and it tells us that there is heavy call writing detected at 315. That's a top ceiling for bulls, and the put accumulation at 305. So this is the floor. So now I don't have to like go into this. I mean, we can look at the details if you want, but otherwise, this is a nice summary it gives us. So same thing, it can also give us for the ETF. We can try some ETF, for example. So the way it works is the same thing. The logic is the same thing. It when we looking at something here, it picks up from the change in URL. This is because this is single page uh, applications, TradingView. So we have to detect it actually what we are looking here. And this the whole way of doing this, like on page load kind of thing, that may not work for us to get, because this is a separate this is a separate thing, this is a separate thing. So I'll show you the programming also, like how this is how this thing works. Uh, but so the way we have built this, I mean, I'll show you at a high level what's the uh, I have used the uh, Copilot. I mean, I've used the anti-gravity, and actually started with just one simple command, like I built this MCP config file, and then I just stayed slash plan. It started planning everything. This was a very fun experience building with this using anti-gravity. And then I was talking, like as we are like two friends are working together, trying to build something, and it was overall very good experience. And it started, like and then it built something, and I'll say, okay, can we change this to this, and I want this thing, and then again it will quickly like change it. And because I like front end code, I don't know. So it was like it was writing everything in the front end very uh, quickly. Um, so this was one thing. Another thing is, I for changes and like how it is doing and what I need to change, I opened the IDE from here. This is anti-gravity 2.0.10, and so I use this to look at the code. And this is like some of the code here. This is the main.py file. This is all this code is discussed in much detail. There is a like it's a combination of the way I have designed this entire video is first I'm showing you the demo, and then and I'm showing you a little bit of code here because the code is detailed, discussed in very much detail in the second video. In the like There's a 5 minutes, 7 minutes of overview, and then there is a podcast which discusses it reviews, done as a peer review, and then it discusses all the what I did, and what I missed, or what should I have done better, and all that thing is discussed in much detail. It's very fun to it will be fun to watch it if you are a data science student, and if you want to do this as a project for your portfolio, you can show it as a financial systems AI app you have built, and you can use this as a framework or as a template for you can convert this uh, into a uh, cryptocurrency, uh, like Copilot for cryptocurrency. Like if you can show the cryptocurrency data here. Uh, Actually, for this one, like if I show you the code, a little bit of code to discuss, then so I tried various many different data providers. I wanted to My first solution design was like so here coding is a little bit less for us. We are more of working as a solution designer or solution architect. We are mostly doing the software engineering work here. So, I tried several solution space I wanted to explore. I was thinking that there should be some good MCP servers which can give me the data, because I was more concerned with like getting the more reliable, accurate data, and I also wanted to get it for free. So I tried many MCP servers, uh, and there's some code here. I'm not opening this because I want to show the key and all. But so I tried this several things, but then I thought that it was they were asking some financially it was not viable for me to get this to build this get their subscription and pay the money and all that thing. So then I finally reverted back to the Yahoo Finance, and so I built this with Yahoo Finance. And so the way this thing works is I'm using FastAPI for the MCP, and the main part is to get the options data. We are from the ticker, because we are getting the ticker from the URL. And then for if it's, I was trying to build it for NSE, ETSX, and for other exchanges as well. But I found out that Yahoo mostly has for US market it has a lot of data available. For other markets, it's not. I mean, I may have to do something, but when I was doing it, I tried to do it. But at the same time, I tried the commodity markets, so the gold and other things are showing up for us. So I tried to do it with this ETF to get it, uh, because otherwise this data I may not be able to get it for free. So this is done with ETF route here, and so yeah, this is so then this just how do we do the produce the summary basically. So based on the open interest, we are checking the how much is open interest and all. Then we are producing the summary here. So this is the backend, which so this backend is like to understand the whole thing, like the big picture is this is the main backend data provider, our MCP server, and so this component. So the way it works is this component will continuously ping this component for if there is any what ticker somebody is looking at. The moment it finds out, okay, somebody's looking at a new ticker, then it will try to uh, change it to provide data for that one. Like say for example, we are looking at the gold right now, and so we see that it changed it to the. We are looking at this exchange and GC1 here. So it tries to send the request the data to our main.py file, which in turn gets the data from Yahoo Finance, and it produces a summary, which the front end here is displaying it here in this Chrome extension. So this is pretty much the overall design wise, but there are some other. If you are when you are building it, uh, you can work somewhat similar, but I'll also show you the other part was like, so I have the uh, so these files are so these are the files it produced for the front end, and so for the Chrome extension. So it will in detail it will talk about what file you will change. Uh, This is the main logic for the regex. So when we are looking at this, we talked about like how do we get it from the URL. So this is it will try to match using the regex, and then there is a another thing I wanted to discuss was, so yeah, these are the some of the files it has produced for the to display the to create the front end. So yeah, I'll provide all these files in the GitHub. You can modify these files, and the way it's working here is like so the way it works is this anti-gravity. Okay, so when we are I'll just show you how it works. So the main so this is a different folder I have put it here because the Chrome extension was not taking the files from here, from the anti-gravity this folder, where the anti-gravity mainly build the other programs. So I have to put it into two different folders. This one thing that you might encounter this thing. So the way this thing works is like, say, when I have this main program here, well, basically I'll run the Python main file. So this is what it's going to start the server. So once the server is started here, then we can go to the like we can go to like say we are here on our trading view. Then we'll go to the extension and we start the extension from here. And the extension will come here. This is the default. So because it falls every 1 minute, this is in a continuously it's polling that what we are looking at. Then it will tell us that okay, the moment it picks up that okay, we are looking here, it will send it to the backend with the data and display it here. So this is how it works basically. So now the next two sections are, as I said, like there's a video summary and then there's a podcast. And yeah, that's it. Hope you will enjoy it. Thank you.
Welcome to this explainer. Okay, today we are cracking the code on a major headache for developers. We're going to break down exactly how to build a production-grade, real-time AI trading tool, and we're going to do it without spending a single dime on expensive data subscriptions. So if you're completely tired of fragile scripts and really want to master enterprise-grade architecture, you are definitely in the right place. Let's get into it. Right off the bat, here is the core problem. Most traders really want real-time options chain analysis to find market support and resistance, right? But to actually get that data, you're usually trapped. You either slam into a brick wall of massive monthly API paywalls, often upwards of $200 a month, or worse, you resort to some sketchy browser extension that essentially asks for the keys to your brokerage account. Honestly, neither is a great choice. So we obviously need a better way. Enter the TradingView Options Copilot. It is 100% free, highly secure, and entirely production ready. But here is the real secret. We aren't just writing a flimsy web scraper here. We are actually building a multi-layered architecture that serves as a universal framework. If you master this stack, it's like having a master key. You can build virtually any AI agent you can dream up. Here is our architectural blueprint for today. We'll cover the market data problem, the secure cloud dev environment, the front-end SPA sniffer, bridging browser isolation, Python brain commodity rerouting, and wrap up with the universal AI template. Let's dive in.
Section 1. Secure Cloud Dev Environment. So, building a local public extension is actually a massive risk. Literally one wrong move and your API keys are out in the wild for anyone to grab. That is exactly why we use Google Anti-Gravity and Cloud Workstations. By developing entirely inside this managed cloud IDE, all your sensitive logic and critical files, like your mcp_config.json, stay completely locked down in an isolated environment. Your credentials just act as local environment variables, totally cut off from the public web, safe and sound.
Section 2. The Front-End SPA Sniffer. Moving to the front end, we immediately face our first major technical monster. TradingView is lightning fast because it is a single-page application, or SPA. That means the URL seamlessly shifts from, say, Apple to HDFC Bank, without ever actually reloading the web page. Now, for a standard Manifest v3 Chrome extension, this is a total nightmare. Traditional content scripts only wake up on a fresh page load. So when a user clicks a new ticker, the old extension just sits there, completely oblivious to the change.
So how do we outsmart it? Well, our genius engineering fix here is a background interval sniffer built right into our content.js file. Think of it kind of like a night watchman. Instead of waiting for a full page reload, we use setInterval to actively check the location.href every 1,000 milliseconds. The absolute second it detects a URL change, it uses a regular expression to grab the new stock ticker and instantly fires off our update logic to the side panel. It's lightweight, it's invisible, and it is completely SPA-proof.
Section 3. Bridging Browser Isolation. Okay, so we have our ticker. But now, we hit the strict security protocols of Manifest v3. Chrome uses something called browser isolation. Your content.js script might live on the web page, but it's completely trapped there. It is strictly blocked from talking directly to our heavy-duty local Python backend. No direct calls allowed, no heavy data processing. It is literally on an island.
To bridge this gap, we rely on runtime messaging. Our content script extracts the ticker, let's say it's Reliance, and uses the chrome.runtime.send message API. This acts as our secure courier, passing the data straight to our sidepanel.js script. Now, because the side panel acts as the actual user interface of the extension, it actually has the clearance to make external network calls. It grabs the ticker and fires a secure HTTP GET request straight over to our local FastAPI Python brain. It's a perfectly secure, isolated relay system.
Section 4. Python Brain Commodity Rerouting.
Now that our Python brain, which is operating in main.py, actually has the data, we have to make it work using completely free sources. And this is the crucial point. When pulling from free APIs like Yahoo Finance, we hit a massive wall with commodities. These free sources usually just choke on illiquid or complex future symbols like COMEXGC1 for gold or NYMXCL1 for crude oil. If we just feed those raw symbols directly to our backend, the API crashes and gives us absolutely nothing. To completely bypass this, we use dynamic commodity rerouting right inside main.py. We intercept the incoming illiquid ticker, use a simple Python list comprehension to strip away the special characters, so turning GC1 into pure GC, and then we logically shunt these obscure futures into their highly liquid US ETF equivalents. Gold futures become GLD. Crude oil becomes USO. Silver becomes SLV. By analyzing the ETF options chain instead, we trick the system into giving us perfect, real-time volume and sentiment data that mirrors the futures market perfectly, entirely for free. This clever back-end rerouting is seriously the magic bullet. It results in a 100% free, real-time options sentiment analysis tool. By letting Pandas do all the heavy mathematical lifting locally to find maximum call and put open interest, we generate the exact same powerful insights that usually require premium broker subscriptions. This little trick alone saves you a massive chunk of change.
Section 5. The Universal AI Template. Because this entire setup is incredibly secure, entirely free, and beautifully handles single-page applications, developers can treat it as a true universal framework. It goes way beyond just options trading. You can take this exact blueprint, swap out the main.py brain and the URL targeting in the sniffer and build whatever you want. Want a crypto intelligence copilot? Just match Binance URLs and plug in the CCXT Python library. Building a sentiment and news copilot? Grab the stock ticker from the URL and use beautiful soup to scrape live sentiment.
So, you now understand the full universal.
Imagine leaving the keys in the ignition of a Ferrari, right?
with the doors completely unlocked, just parked in a bad neighborhood.
Oh, yeah. That's a disaster waiting to happen.
Exactly. And that is exactly what thousands of developers do every single day
Yeah.
when they build Chrome extensions for financial trading. I mean, they just drop their live broker API keys straight into the front-end code, push to the web store, and just, pray nobody opens the developer tools to steal them.
It is a shockingly common anti-pattern, actually. And once those keys are compromised, automated bots can scrape them in seconds.
Right.
Depending on the permissions attached to that API key, a bad actor could execute unauthorized trades or, liquidate an entire portfolio.
Yeah.
Or honestly, simply run up a massive bill by maxing out the data request limits before the developer even wakes up.
Which is terrifying. But today, we're looking at a developer who did not do that. Instead, they built a fortress. Welcome to the deep dive.
Glad to be here for this one.
If you are joining us today, I want you to be prepared, because we are setting a very specific tone. This is not a casual 1,000-foot overview. Consider this a professional peer-to-peer code review.
Yeah, grab a coffee, pull up the terminal in your mind, because we are doing a full architectural teardown.
We are getting under the hood of a system that solves some notoriously difficult problems in modern web development. The mission for today is to review the architecture of a custom-built AI options chain explainer app. The developer calls it a context-aware trading copilot side panel.
That's quite the name.
It's a mouthful, yeah. But our sources for this review are incredibly dense. We are pulling from actual developer logs, the architecture diagrams for a framework they've dubbed the Anti-Gravity Bridge, the official Google Anti-Gravity 2.0 documentation.
Plus the cloud workstations manuals.
Right. And a highly detailed developer guide from the DEV community focused specifically on Manifest v3.
The combination of those sources gives us, a perfect cross-section. We get to see the strict, sometimes super frustrating constraints of front-end browser extensions colliding with some genuinely ingenious back-end problem solving.
And look, if you are listening to this and thinking, well, I don't trade financial options, why do I care? I need you to stick around.
Yeah.
Because this is not actually a deep dive about finance.
No, not at all. That is just the wrapper.
Exactly. This is a masterclass in modern software engineering. It's about how to bypass incredibly expensive enterprise API paywalls using clever data proxies. It is about navigating the completely hostile environment of the modern browser.
And most importantly, it's about building a secure, universal AI assistant template, one that you could repurpose for almost anything like tracking crypto whales or analyzing news sentiment in under an hour.
The options trading functionality is merely the proof of concept. The underlying architecture, the way they decouple the browser from the data, that is the real focus here. Let us start at the very foundation, the development environment itself. Because you can't build a secure application on a compromised machine.
Right. The logs show this project was scaffolded using Google Anti-Gravity 2.0.
Which represents a fundamental shift in how we think about writing code.
Yeah.
I mean, traditional integrated development environments, IDEs, they were just fancy text editors running locally on your laptop.
Yeah, but Anti-Gravity 2.0 is an agent-first platform. It is designed from the ground up to allow AI coding assistants to interact deeply with the browser, the terminal, and the file system.
But the security architecture is what really stood out to me. The documentation emphasizes that this application was developed with extreme safety in mind. Going back to my Ferrari analogy, if putting broker credentials like an interactive brokers or Zero the token into a Chrome extension is leaving the keys in the ignition, how does this architecture secure the car?
By never bringing the car to the neighborhood in the first place.
Wow. Okay, explain that.
Well, this architecture completely removes the keys from the front-end environment. Instead of the Chrome extension reaching out directly to the financial markets, everything operates through a secure, local Python FastAPI backend.
Okay, I want to break down FastAPI for anyone listening who hasn't used it. Think of an API like a digital menu at a restaurant. The Chrome extension is the customer looking at the menu, and FastAPI is the framework used to build the kitchen that receives the order and cooks the food.
That's a great way to put it.
It is incredibly fast, it's written in Python, and in this setup, it acts as a highly trained bouncer. The Chrome extension never actually sees the API keys. It just walks up to the bouncer and says, hey, I need data for Apple stock.
And the bouncer then turns around, goes into a locked vault that the extension cannot access, retrieves the data using the secret keys, and hands a clean, sanitized package of data back out to the extension.
And to understand how that vault works, we need to look at the Model Context Protocol, or MCP, right?
Exactly. The developer logs spend a lot of time on this. They talk about setting up an MCP config JSON file.
So what is the actual mechanism of an MCP server?
Think of MCP as a universal translator, or like a diplomat. Historically, if you wanted an AI agent to read data from a specific database or a live API, you had to write custom, often really fragile integration code.
And every time the data source updated its format, your code broke.
Every single time. But the Model Context Protocol creates a standardized bridge. It allows the AI agent running inside anti-gravity to query an external data source using a uniform language.
But where do the keys actually live? Because the logs explicitly mention a massive API key being used early on in the project.
Right, massive API.
Which is a major financial data provider. Where is that key physically stored if it is not in the browser?
It lives strictly locally. Inside that MCP config JSON file on the backend server, the critical security boundary here is isolation.
Okay.
That JSON file is never exposed to the public internet. Furthermore, it is completely invisible to the browser's document object model, the DOM.
Let us clarify the DOM for a second. If the HTML of a web page is the original architectural sketch of a house, the DOM is the live, real-time house after it has been built. It is what JavaScript interacts with to change colors, move buttons, or read text on the screen.
Exactly. And because Chrome extensions live inside the browser, they're intimately connected to the DOM. If you put a secret key in your front-end code, it will eventually end up in the memory space associated with that DOM.
Where a malicious script or a compromised third-party library could potentially scrape it.
Precisely. By keeping the keys in the MCP config on the Python backend, the extension operates in complete ignorance. It does not know how the data is fetched. It does not know what credentials are used.
It just sends a ticker symbol and waits for a JSON response.
Yep. This mirrors enterprise-grade software supply chain security perfectly. The sources include manuals for Google Cloud Workstations, and the parallels there are obvious.
Because enterprise companies do not want source code and production credentials sitting on a junior developer's personal laptop, which, they might leave at a coffee shop.
Right. They rely on managed development environments. Cloud workstations utilize ephemeral virtual machines.
Let's define ephemeral in this context. We're talking about a computer that physically materializes in a data center when a developer logs in and completely vaporizes the second they log out.
Right. Vaporizes is a good word for it. You spin up a pristine, standardized Linux environment, but to ensure the developer doesn't lose their progress every time they log out, you attach a persistent storage volume to that ephemeral VM.
Oh, I see.
This guarantees that the operating system and the dependency tree are fresh and uncompromised every single session, but the actual code changes remain saved.
So in this project, the developer is running the FastAPI backend inside an anti-gravity environment, which can be hosted on one of these secure cloud workstations. You have Gemini Code Assist running directly inside that perimeter.
The resulting security posture is formidable. You have an AI assistant writing code in a vaporizing virtual machine, connecting to financial APIs using local-only MCP configurations, and feeding that data to a browser extension that has absolutely zero awareness of the underlying credentials.
It's bulletproof. So we have established this incredibly secure bouncer in the backend. The backend is locked down in a Python fortress.
Yeah.
But a backend is useless if the user cannot interact with it. We need a front door. And building a front door in Chrome today means stepping into the absolute minefield that is Manifest v3.
Oh, man. Manifest v3.
Looking at the logs, the developers had to navigate some brutal constraints here. It is honestly refreshing to see a side panel app built this well.
Manifest v3, or MV3, it represents a tectonic shift in browser architecture. To understand why it is so strict, we have to look at the history of Manifest v2.
MV2 was the Wild West.
It really was. Under Manifest v2, developers had access to something called background pages. A background page was essentially a hidden, invisible browser tab that launched when Chrome opened and ran continuously in the background until Chrome was closed.
Now, as a developer, that sounds incredibly convenient. If I am building an options trading extension, I just write a script that opens a WebSocket connection to my broker, put it in the background page, and it just sits there monitoring prices all day.
It was incredibly convenient for developers, but it was disastrous for users. Imagine having 20 extensions installed, all running hidden background pages simultaneously.
Oh, the RAM.
Right. The browser's RAM usage would skyrocket. The CPU would constantly be processing invisible tasks. It made Chrome notoriously sluggish.
And beyond performance, the security implications were terrifying.
That is the core reason Google killed MV2. A compromised background page had persistent, unrestricted access. If a bad actor bought a popular extension, pushed a malicious update, and hijacked that background page, They could silently monitor network traffic.
Or like mine cryptocurrency on the user's machine indefinitely.
Exactly. So in Manifest v3, background pages are entirely dead. You cannot use them.
The DEV community guide in our sources breaks down the replacement. Service workers. And the lifecycle change here is drastic. The guide notes that service workers are completely event-driven, and critically, they terminate after 30 seconds of inactivity.
30 seconds?
Wait, 30 seconds. If I am building a trading copilot that needs to monitor volatile markets and my background process is being assassinated by the browser every half a minute, doesn't that completely break the application? How do you maintain state?
It forces a completely different engineering paradigm. You just can't rely on long-lived connections or keeping variables in global memory because that memory gets wiped every 30 seconds.
Wow.
Instead, the service worker must be designed to wake up only when a specific event occurs, like the user clicking a button or a network request completing. It performs its task, saves any necessary state to a persistent storage API, and gracefully goes back to sleep.
It's like having kitchen staff that completely evacuates the building the moment there are no active food orders, and then rushes back in, puts on their aprons, and looks at a logbook to remember what they were doing the second a new order prints.
That is a highly accurate way to visualize it. The browser's V8 JavaScript engine reallocates that memory instantly. It is a massive win for laptop battery life and overall browser performance.
The DEV community guide mentions another huge security restriction in MV3. The ban on remotely hosted code.
Yeah, this is huge. In the past, an extension could dynamically pull down a fresh JavaScript library from a content delivery network, a CDN, at runtime.
So a developer could submit a completely innocent-looking extension to the Chrome Web Store, get it approved, and then just flip a switch on their remote server to inject malicious code into the extension after the fact.
Exactly. Manifest v3 fundamentally outlaws that. Every single line of code, every library, every script that the extension executes must be bundled directly within the extension package itself.
No exceptions.
No exceptions. This guarantees that the exact code reviewed by Google's automated systems is the code running on the user's machine.
But this strictness introduces serious architectural hurdles. The logs detail a major failure point regarding browser isolation. Let us look at the structure of this Copilot app. You have a content.js script, which is injected directly into the web page the user is looking at, in this case, TradingView.com.
Right.
And then you have sidepanel.js, which controls the UI in the dedicated Chrome side panel.
And architecturally, Chrome treats those two scripts as if they are running on completely different planets.
The developer tried something that seems logically sound at first. They had the content.js script look at the TradingView page, find the stock ticker, say Tesla, and save it to the browser's local storage. They then told the side panel to read that local storage to display the options chain for Tesla.
And it failed completely.
It did. Why?
Because local storage is partitioned by origin. The content.js script is operating in the context of TradingView.com. When it writes to local storage, it writes to TradingView's isolated silo. The side panel, however, operates in the context of the Chrome extension ID. It has its own entirely separate local storage silo. When the side panel looked for the ticker symbol, it saw nothing.
They were basically shouting across a vacuum. So how do they bridge the gap?
They utilized the standard MV3 solution, runtime messaging, specifically the chrome.runtime.sendMessage API.
I picture this like a pneumatic tube system built into the walls of the browser. The developers refactored the content.js script to act simply as a sniffer. Its sole purpose is to sit inside the TradingView DOM, grab the ticker symbol from the URL, put it in a capsule, and shoot it through the pneumatic tube to the side panel.
The side panel, which has a listener set up, receives the capsule, extracts the ticker symbol, and then turns around and triggers the FastAPI backend to fetch the options data. It is an elegant decoupling of responsibilities.
The content script handles DOM awareness, and the side panel handles the UI and the backend communication. But while looking through the manifest.json file and logs, I noticed something about permissions that I want to question. When you declare a content script, you have to tell Chrome which websites it is allowed to run on using an array called matches.
The URL match patterns.
Yeah, right. Now, I have looked at dozens of extension tutorials, and almost all of them just tell you to put all URLs in brackets in that array. It basically asks for permission to inject the script into every single website the user ever visits. It is incredibly easy to develop with.
Sure.
But in this project, they wrote out the full TradingView URL with a wildcard just for the symbols path. Why would they intentionally restrict themselves and go through the hassle of being that specific? What if they want to support Yahoo Finance later?
Using that all URLs tag is one of the biggest red flags you can trigger during the Chrome Web Store review process.
Really? I assumed it was just standard practice.
It is a standard practice that Google is actively trying to eradicate. The DEV community guide makes this very clear. Permissions in Manifest v3 are deeply granular. If you request all URLs, you are not just asking to see TradingView. You are demanding the ability to read and modify the user's online banking portal, their encrypted email client, and their private healthcare dashboards.
And an options trading explainer has absolutely no legitimate business touching a banking website.
None. When the automated web store review system sees that global permission requested by a simple utility app, it halts the process.
It just stops it.
Yep. The extension is flagged, delayed for manual human review, and almost universally rejected unless the developer provides a highly technical, documented justification for why global read and write access is strictly necessary for core functionality.
So by targeting only TradingView symbols using that specific wildcard path, they're not just being tidy, they're practicing the principle of least privilege.
It ensures immediate approval in the web store. And furthermore, it builds massive trust with the end user. When someone installs this extension, Chrome will display a prompt that says, "This extension can read and change your data on www.tradingview.com."
That is a very different psychological barrier than seeing this extension can read and change your data on all websites.
Absolutely.
Okay, so the front end is playing by the rules. It uses runtime messaging to cross the isolated contexts and requests the absolute minimum permissions required. The sniffer script is sitting on TradingView ready to grab the URL and pass it to the side panel. But reading the URL on a modern website is a surprisingly difficult problem.
It brings us to the complexities of the modern front-end framework.
If you have ever tried to write a simple script to scrape data from a modern website, you know the absolute nightmare we are about to discuss. Let us dive into the SPA challenge.
Single-page applications.
TradingView is an SPA. Now, 20 years ago, the web was simple. If you were on Yahoo Finance looking at Apple stock and you clicked a link for NVIDIA, your browser would send a request to the server. The screen would flash white, a little loading spinner would turn in the tab, and the server would send back a completely new, freshly baked HTML document.
Right. And in that legacy architecture, building an extension was trivial. Your content.js script would simply rely on the window.onload JavaScript event listener.
Because it reloaded every time.
Exactly. Every time the page flashed and reloaded, the event fired, your script ran, grabbed the new URL, and updated the side panel. It was entirely predictable.
But single-page applications destroyed that predictability. In a modern framework like React or Angular, which is what TradingView uses, the initial HTML document is just a hollow shell. When you click from Apple to NVIDIA, the URL in the address bar changes, yes, but the page itself does not reload.
The JavaScript engine intercepts the user's click. It stops the browser from making a full navigation request. Instead, it fires off an invisible background request. An AJAX, or fetch call to an API, pulls down a tiny JSON package of NVIDIA's pricing data and dynamically rewires the DOM in real time to replace the Apple charts with NVIDIA charts.
To the human eye, it looks instantaneous and smooth. But to the browser extension, it is a catastrophic synchronization failure. Because the window never technically reloaded, that window.onload event never fires.
The extension is left entirely in the dark. The user is now actively analyzing NVIDIA's chart, but the Copilot side panel is stubbornly displaying the options data for Apple because no mechanism ever notified it that the context had shifted.
The developer logs show them hitting their head against the desk over this exact bug. They tried attaching event listeners to the specific navigation buttons on the TradingView interface.
Which is a highly brittle approach.
I would think it's logical. Just listen for a click on the search bar.
Yeah. Logical, but extremely fragile. Modern obfuscated platforms like TradingView change their CSS class names and DOM structures constantly during routine updates. If you attach a listener to a button class called search-icon-v2, and TradingView pushes an update tomorrow, renaming it to nav-search-bar, your entire extension breaks silently.
So they needed a solution that ignored the UI entirely.
Yeah.
And I was looking through the content.js code, and I saw what they implemented. Honestly, at first glance, it looks like a hack. It looks like lazy coding. They implemented a set interval sniffer.
Polling is often considered an anti-pattern in software engineering, but in this specific browser context, it is brilliantly pragmatic.
Let me explain the mechanics of what they did, and then you explain why it isn't terrible practice. In the JavaScript, they declare a variable called lateral and set it to whatever the location.ref, the current web address, happens to be. Then, they use setInterval to create an infinite loop that executes a tiny block of code every 1,000 milliseconds.
Every second.
Right. Every single second, the loop wakes up, checks the current address bar, and compares it to the lateral variable. If they are identical, the loop goes back to sleep.
It does nothing.
But if the user clicked a new stock, the SPA rewrote the page and the address bar changed. The loop wakes up, compares the new address to lateral, realizes they do not match, and the alarm trips. It updates lateral to the new string and fires that pneumatic tube message to the side panel saying, hey, the user moved. Fetch new data.
Exactly.
But isn't it incredibly inefficient to have a script waking up every second forever?
In a traditional server environment, continuous polling can be resource intensive. But we have to look at the mechanics of the browser's JavaScript event loop. Comparing two short text strings takes a fraction of a millisecond.
Oh, okay.
The computational cost of waking up, evaluating an if statement on two strings, and returning to a dormant state is statistically negligible to a modern CPU.
It's not going to drain a laptop battery.
Not even measurably. The alternative, setting up a complex mutation observer that watches the entire DOM for thousands of microscopic changes every time a chart tick updates, that would consume vastly more memory and CPU cycles. The URL is the ultimate unobfuscated source of truth. By checking it directly, the set interval sniffer becomes completely immune to TradingView's UI changes.
I compare this to a security system. Relying on a click listener is like installing a magnetic sensor on a window. It works perfectly unless the burglar figures out how to cut the glass without separating the magnet.
Right.
But the SPA sniffer, that is like paying a guard to physically walk the perimeter every single second, checking the physical locks. It requires slightly more effort from the guard, but it guarantees that nothing, absolutely nothing, slips by. It's so refreshing to see a side panel app that doesn't just crash on SPA transitions because they use this slick set interval sniffer.
It is a fail-safe mechanism. It ensures absolute state synchronization during fast SPA transitions. The side panel will never display stale options data because the interval sniffer will catch the URL change within a maximum of 1 second.
Okay, the front-end architecture is solved. We have successfully navigated MV3's draconian security. We've built a robust interval sniffer that bypasses the SPA trap. The content.js script grabs the correct ticker symbol and fires it back to our FastAPI bouncer. The data is flowing.
The infrastructure is solid. Now we encounter the business logic.
Exactly. This is where the project transitions from solid front-end engineering to what I consider exceptional back-end problem-solving. We're entering the genius move segment of the logs. Let us talk about dynamic rerouting and the massive systemic data gap in the financial industry.
The logs reveal a significant pivot midway through development.
They started by hooking up the MCP server to the massive API, which many developers might know by its former name, Polygon.io. It is a phenomenal service, providing institutional-grade financial data. But the developers hit a massive wall, the free tier.
Financial APIs are notoriously expensive. The free tiers exist strictly for testing syntax, not for powering live applications.
The developers found that the free tier endpoints often suppress live volume data. And if you are building an options chain explainer, volume is the entire ballgame. You cannot identify strong support and resistance levels without knowing where the heavy volume of contracts is sitting.
Without volume, an options chain is just a list of theoretical prices. It's useless.
Furthermore, the massive API free tier completely locked them out of international exchanges. If a user tried to analyze a stock on the National Stock Exchange in India or the TSX in Canada, the API just rejected the request.
The developer faced a classic sauce dilemma here. When you hit the data paywall, you typically have to pass that cost on to your users. You force them to create an account and pay a monthly subscription so you can afford the API overhead.
But they refused to do that. They executed a major pivot. They ripped out the expensive API integration entirely. They refactored their Python backend to use yfinance, Yahoo Finance.
yfinance is an open-source Python library that essentially scrapes the public-facing endpoints of Yahoo's financial web pages.
It instantly made the application 100% free. And from a security standpoint, it was brilliant because suddenly there were absolutely no API keys to manage or protect. The MCP config JSON did not need a secret token anymore. The bouncer was just pulling public data.
It democratizes the application. But relying on public web scrapers introduces a new, highly specific set of challenges, particularly when dealing with derivatives.
Right, because Yahoo Finance is fantastic for standard equities. If you pass it the string AAPL, it returns Apple's options chain flawlessly. It handles standard ETFs perfectly, but it chokes hard on raw, illiquid futures tickers.
To understand why this creates a fatal error in the app, we need to understand how futures data is gatekept.
The logs show a perfect example of the failure. The user is on TradingView, looking at gold futures. The Chrome extension sniffer grabs the URL and extracts the raw string COMEX-GC1! It passes that ugly string to the Python backend. The backend hands it to yfinance, and Yahoo just throws a 404 error, returning a completely empty dataset. Why is finding options data for Apple completely free, but finding it for gold futures is impossible?
Because institutional futures data is not public property. It is heavily paywalled and aggressively protected by the exchanges themselves. Entities like the CME Group, the NYMEX, and the COMEX.
They own the raw numbers.
Precisely. If a proprietary trading firm wants a direct, low-latency feed of raw futures and options F&O data, they have to pay thousands of dollars a month in licensing fees per user. They have to integrate complex infrastructure like the FEX protocol, or pay for server co-location directly inside the exchange's data center.
Which is why a Bloomberg terminal costs $24,000 a year. You are paying for that clean, latency-free options data.
Free, public-facing portals like Yahoo Finance simply do not have the legal rights or the technical infrastructure to distribute institutional F&O data cleanly. When they do attempt to display it, the volume metrics are often suppressed, intentionally delayed by 15 minutes, or formatted so poorly that an automated Python script cannot parse it without crashing.
So imagine you are the developer. Your front end is perfect, your back-end API is fast, but your app is entirely broken the second a user tries to analyze a commodity like gold or crude oil. Most developers would just throw up their hands.
Yeah.
They would write a little conditional statement that says, sorry, commodities are only available on the premium $99 a month tier.
It is definitely the easiest path forward.
But they did not do that. And this brings me to my absolute favorite part of the source material. I need to go on a rant here about the mapping logic, because what this developer pulled off is the ultimate hacker move.
The string sanitization and dynamic rerouting.
Yes. Let us open up main.py and break down how clever this Python logic is. The backend receives this ugly raw futures ticker from the front-end COMEX-GC1! The first thing it does is sanitize the data.
Because raw data from a URL can never be trusted to conform to an API's expectations.
Exactly. They wrote a single line of Python using a list comprehension. Clean symbol equals empty string.join, open bracket, char for char, in symbol if char.isalpha, close bracket. Let's explain what that does mechanically.
It takes the string GC1! And iterates through it character by character. The isalpha function checks if the character is a letter. If it is a letter like G or C, it keeps it. If it is a number or a symbol like the 1 or the exclamation point, it discards it.
Okay.
The join method then stitches the remaining letters back together.
It is so concise. It rips out all the confusing contract month numbers and punctuation, leaving just the pure alphabetic core of the commodity. GC.
Once the string is sanitized, the brain of the backend, the dynamic rerouting module, takes over.
And this is where the magic happens. The Python code enters an if-else block. It checks the exchange and the clean symbol. If it sees the exchange is COMEX and the symbol is GC, which is gold, it does not ask Yahoo Finance for gold futures. It knows that will fail. Instead, it dynamically reroutes the query, fundamentally altering the request in transit, and asks Yahoo for GLD.
GLD being the ticker symbol for the SPDR Gold Shares ETF.
Exactly. If the incoming symbol from TradingView is silver, SI, the Python script dynamically routes the query to SLV. If the user is looking at crude oil, CL, the script maps the request to USO.
Structurally, this relies on a deep understanding of market mechanics. The developer recognized that those specific exchange-traded funds, GLD, SLV, USO, are explicitly engineered by financial institutions to perfectly mirror the price action of the underlying futures market.
How perfect of a mirror are we talking about? Like, is it close enough for real analysis?
Extremely close. Through a process involving authorized participants who constantly arbitrage the difference between the ETF's share price and the physical commodity, the ETF's chart will essentially overlay the futures chart tick for tick.
But the critical difference for our developer is regulatory.
Exactly. Because these ETFs are traded as standard equities on the New York Stock Exchange, they are not subject to the draconian COMEX or NYMEX data paywalls. Their options chains are highly liquid, incredibly active, and the data flows freely into Yahoo Finance.
It is the ultimate backdoor. By mapping COMEX-GC1 exclamation point to GLD into simple Python script, the developer is providing enterprise-level premium sentiment analysis to the user for absolutely free. The application analyzes the massive call input wall sitting on the ETF to infer the sentiment of the institutional futures market, because the two are inextricably linked.
The user experience remains completely seamless. The user clicks on a gold futures chart in TradingView. The side panel spins for half a second, and then outputs detailed support and resistance levels. The user had no idea that the backend just performed a sleight of hand to fetch ETF data instead.
You know what this is like. I love this analogy. Imagine wanting to know the exact temperature outside, but the official, highly calibrated meteorological weather station in your city has erected a paywall, and they want to charge you $5,000 a month for access to their real-time thermometer feed.
A steep price for a simple metric.
Most developers would just tell the users, sorry, I can't afford the weather data. But this developer, they just look out the window to see what kind of coat people are wearing on the street. The coat is the ETF. Observing the secondary market tells you the exact same fundamental truth. It's freezing outside for absolutely free.
It proves that you do not always need the raw, expensive data if you can find a free proxy that exhibits the exact same behavior.
It is so clever. And this ingenious separation of concerns, having the front end act only as a dumb sniffer that grabs a URL, and having the back end act as the brain that sanitizes the data and handles the proxy mapping. It means this architecture isn't just limited to stock options.
Which brings us to the broader implications documented in the sources. The architecture is modular by design.
Yes. Let us zoom out and look at the universal framework. The architecture documentation does not call this project an options app. It explicitly refers to it as the anti-gravity bridge. Scalable architecture for Chrome extensions. It was designed from the ground up to be a universal template.
Because the heavy computational lifting and the API logic are abstracted entirely to the FastAPI backend, the front-end extension remains incredibly lightweight and agnostic.
Exactly. Let's say a student or junior developer wants to build an entirely different product. They can take this exact code base, this secure bridge, and completely change the app's purpose in under an hour. They only have to modify 2 layers. First, they change the URL matching regex in content.js to look at a different website. Second, they swap out the Python library being imported in main.py.
The documentation actually pitches several alternative implementations. Let us break down the sentiment and news Copilot example.
Okay, so you keep the TradingView SPA sniffer exactly as it is. It grabs the stock ticker, say Apple, and sends it to the FastAPI backend. But you delete yfinance. Instead, your Python backend imports a library like Beautiful Soup to scrape the web, or it simply pulls an open Google News RSS feed.
The backend fetches the last 10 headlines mentioning Apple.
Right. And then, utilizing the MCP server integration we discussed at the very beginning, the backend passes those raw headlines to a local LLM running in anti-gravity. It asks the AI for a natural language processing sentiment score. Are these headlines bullish or bearish? Summarize them in 3 bullet points.
The Python backend then takes that clean, AI-generated summary and sends it back through the pneumatic tube to the Chrome side panel.
The front-end code doesn't change its structure at all.
Yeah.
It just displays a news summary instead of an options table. But the example that really gets me hyped is the whale tracker.
The cryptocurrency application.
Imagine you want to build a crypto monitoring tool. You take the anti-gravity bridge template, you go into manifest.json and content.js, and you change the target URL. Instead of TradingView, you tell the sniffer to monitor URLs on Coinbase or Binance.
So the interval sniffer is now looking for strings like BTC-USD instead of AAPL.
Exactly. Then you open main.py, you delete the options logic, you replace it with CCXT, which is a massive open source Python library designed specifically for interacting with cryptocurrency exchange APIs. You write maybe 15 lines of Python to fetch the live crypto order book for Bitcoin. You have the backend identify where the massive buy walls and sell walls are located, the so-called whales manipulating the price.
The backend calculates the pressure, formats it into a clean UI payload, and pushes that analysis to the side panel.
You could have a live, enterprise-grade crypto whale tracker running securely in a Chrome side panel built over a single Saturday afternoon.
This really forces us to consider the implications of where software engineering is heading. We are entering an era where AI-assisted coding tools like Google Anti-Gravity and Gemini Code Assist are acting as profound force multipliers.
Force multipliers, that's the perfect way to describe it.
10 years ago, building a secure, cross-context browser extension with a dedicated backend API would require a team of specialized developers. You needed a front-end JavaScript expert who deeply understood the eccentricities of Chrome APIs. You needed a back-end engineer configuring the server architecture. You needed a DevOps specialist handling the secure deployment and key management.
And coordinating that team to build a working prototype would take months.
But now, a single developer armed with a clear architectural vision and an AI agent to handle the boilerplate syntax can build a highly secure, enterprise-grade, agent-driven micro-application in days.
Wow.
The heavy lifting is no longer writing the syntax. The heavy lifting is the architectural problem-solving. It is knowing that you need a set interval sniffer to defeat the SPA trap. It is knowing how to map futures to ETFs to bypass paywalls.
The AI can write the Python list comprehension in 1 second, but the human has to realize that the weather station is a ripoff, and they should just look at the coats outside.
The human provides the ingenuity, and the AI provides the velocity.
Let us recap the mechanics of this brilliant journey we've been on. We started by navigating the strict, necessary security constraints of Manifest v3, moving away from the bloated, dangerous background pages of the past to efficient, ephemeral service workers. We examined how runtime messaging acts as a bridge across isolated browser contexts.
We explored how to elegantly hack around the limitations of modern single-page applications, utilizing a lightweight, pragmatic set-interval sniffer to guarantee the application state never goes stale during navigation.
And then we hit the backend, where the developer bypassed institutional data paywalls completely. Not by stealing data, but by dynamically sanitizing and mapping raw futures tickers like COMEX-GC1 to their highly liquid ETF proxy equivalents like GLD.
Ultimately creating a robust, universal framework between a simple browser UI and a powerful Python backend that keeps all credentials secure and invisible.
It is a masterclass in pragmatic engineering. But before we sign off, I want to pose a question based on everything we have unpacked today.
Yeah, let's hear it.
If a simple Python translation layer can bypass expensive data paywalls by finding proxy data like using public ETFs to infer gate-kept futures sentiment, what other hidden free proxies exist on the internet?
That is a great question. We operate under the assumption that high-value data is permanently locked behind enterprise subscriptions, supply chain logistics, real estate trends, consumer sentiment data.
Right.
But if you know how to map it, if you know what secondary markets or public behaviors perfectly correlate with that premium data, how much of the premium internet is actually fully accessible right now, just waiting for the right proxy.
If you are listening to this, I really want you to think about that. That is a fascinating thought to leave on. The data is out there, you just have to know which window to look out of. To everyone listening, thank you for joining us on this incredibly deep dive. I highly encourage you to take the concepts from this anti-gravity bridge template, spin up a secure environment, and go build your own browser copilot. See what proxies you can find.
The digital landscape might be heavily guarded, but with the right architecture and a bit of ingenuity, you don't need to break down the front door. You just need to know how to read the signals from the street.
Catch you on the next one.